I'm very happy to be here today, unfortunately only online. So I'm going to present this work that I'm currently doing together with Sebastian and Marina and Niklas. It's titled Bridging Data and Theory for Monitoring Resilience Changes in Tropical Forests. So we will not only talk about tropical forests and resilience, but also about data. And as you can see in the background, we will mainly talk about satellite data, actually. So before we start, I would like to give a short overview of what we will talk about. We will start to talk about resilience in tropical forests. Actually, Julia already gave a very nice introduction, so we will keep that very short. But we will shortly see why there's empirical evidence and theoretical evidence why there could be high stability, and look at the same study of Chris to see if it's changing. And then we will continue looking at ingredients and potential obstacles of resilience analysis, especially for tropical forests. And of course, there are always two ingredients, namely the resilience metrics and remote sensing products in our case. So yeah, we will look at those two. And then we will look about these vegetation products and compare them to what we expect from theory. And first, we will look at the noise in these products, and then we will look at empirical recovery wherever we can detect it. And then we will try to answer this question that everybody is interested in, like, is there actual resilience change in the tropics, and conclude with a short summary. So, okay, empirical evidence for biostability, we all probably know this. Marina Hirota published it in 2011, where they used the space for time replacement approach and plotted like mean annual precipitation against tree cover for the Amazon, but also for other tropical regions. And you can see that there's like a mean annual precipitation range where there's actually high tree cover state possible, but also low tree cover state. And so that's why we could assume that there might be a tipping happening once we cross like the mean annual precipitation threshold that we see here. That's the main empirical evidence that we have. The main theoretical evidence, Julia also already explained, like the rain is coming in from the Atlantic Ocean, it's transported by the trade winds, and it rains down, like here in the beginning of the Amazon, like the east. And then actually the moisture is taken up by the trees, and they evapotranspirate it back into the air, and then the moisture is transported even further to the west. And that's how the Amazon basin produces enough rainfall to maintain a rainforest in the entire basin. So that's why it's interesting to look at resilience in the Amazon or in tropics in general. And Julia also already mentioned this study by Chris and his colleagues that was published like 2.5 years ago, I think, where they could find like a lot of increase in autocorrelation, which is a measure of resilience change. And so it is possible that like the Amazon rainforest is losing a lot of resilience. But we really want to get robust results. So we should think about like the ingredients that we're actually using for these studies and the potential obstacles that those ingredients can put. So as I said, the first thing that we always use are resilience metrics. And as you might all know, the most common ones are autocorrelation and variance. So what we are usually assuming is that like there's a tipping ahead in our time series that we are like analyzing, and at some point it will tip. Then we usually see like an increase in autocorrelation as well as variance before the tipping is happening. And now in this case, this is an artificial or synthetic time series with white noise. But what was already known, but Andreas and Niklas showed in the study as well, is that like if you have, for example, autocorrelated noise without any tipping, you can also get like an increase in variance and autocorrelation without any tipping being ahead. So that's the first thing we will look at. Like noise can actually influence our resilience metrics, so we should know about our noise in our data. And talking about data, that's always the second thing that we also use for our resilience studies. As I said, in our case, it's remote sensing vegetation products. And probably the most well-known or most used one is the normalized difference vegetation index, short NDVI. And the study by Taylor and Nicholas, they actually looked at this NDVI, calculated trends of lambda calculated from autocorrelation as well from variance, and then looked if this is consistent. And now they found some very interesting thing, namely that basically all the tropical forests, they have either inconsistent or undefined lambdas. So we could conclude from that that either the comparison is problematic of those two, or that NDVI is actually problematic for tropical rainforests. So yeah, we should be careful about the data that we're choosing. There's also another reason why we should be careful, because also Taylor, but with a lot of other colleagues, they showed that for merged vegetation products, we need to be careful. Merged simply means that like we have a lot of sensors collecting data, but we would like to have like a time series as long as possible. So that's obvious idea to just merge it into one that covers the whole time span. And as you can already see here, these are like different sensors. It's actually synthetic, but it represents different sensors. You can see that they all have different signal to noise ratios, and also that like for different time periods, different amount of sensors actually collect the data. So if you merge this now, of course, depending on how you merge it, but you can, in general, it's likely that you have some influence from like the signal to noise ratios and the amount of sensors that you're using. So this blue one here is like the final product that you could get from it. So, and you see it's influencing the variance and the autocorrelation of the product. So you should be very careful about using autocorrelation variance for merged data. Not in general, but as resilience metrics, of course. Yeah, so the goal of this study now is to find out which combination of remotely sensed vegetation products and resilience metrics are suitable for resilience analysis in tropical forests. And yeah, as these are actually the regions that we will look at, so it's only intact forest. We try to exclude human land use here. Yeah, because we want to understand the resilience change in the natural forest or original forest. And we will compare like a lot of different vegetation products from different sensors. So that's just an example so that you can see like merged average time series of like 16 different vegetation products that we will look at. And now, as we said, the first important thing that can influence our resilience metrics is actually the noise of our data. So the idea here was simply to estimate the noise and check its properties. So we simply do this for each grid cell that we have a time series, and for each of these time series, or we have like one time series per vegetation product, we do like some kind of regression. And then with this regression, we get a time series of the noise, and we can analyze the statistics of those time series. Now, the first thing that we are interested in is actually if the noise is white, so if it's not autocorrelated. And so we use the Broich-Godfrey test on those time series that, like the noise time series that I showed before, and we plot here its p-value. And if the p-value is very low, then we can be pretty sure that like the noise is not white, so it's probably autocorrelated. And yeah, these are the results for all of our data sets. And I guess we can conclude from that it's very unlikely that our noise is white for any of the data sets. So we should be careful here. This especially is influencing or could influence the autocorrelation as a resilience matrix. The other thing that we are interested in, or that could like be a problem, is like if the noise amplitude is actually changing over time, this would have a quick influence on the variance. So here we did the same. We estimated noise time series on like sliding windows, and then calculated its amplitude and then the candle tau value of those amplitude time series. And now if this is close to 0, then actually the amplitude is pretty stable or constant. And if it's like 1 or -1, it's the increasing or decreasing respectively. And these are the results. So what I find very interesting here is that like especially the merge data, which are all those that are hatched, so these 7 here, especially for those, you can see that like a constant noise amplitude is pretty unlikely. But to be very honest, also in the other data sets, we do have a lot of cells where the noise amplitude seems to be changing. So also constant noise is not very likely in our data probably, and we should in general be careful about autocorrelation variance when applying them as resilience metrics. That's the noise. So now the question is, how can we actually ensure that the theoretical resilience metrics like autocorrelation variance measure recovery? And this is also nothing new. We came up with the idea of following Taylor's paper and estimate a direct lambda empirical, like the direct empirical recovery rate, wherever we can detect a perturbation. We apply this to all the time series we have, and then we fit like an exponential function. From this, we get like a lambda, which is our recovery rate, and we get like a measure of goodness of fit of this, fit, how well the pink fits the other time series. And then for this, we get like maps for different locations wherever we can detect such perturbations. We get like a lambda empirical, and then we have also our maps of, for example, autocorrelation or variance. And the idea now is simply to check the correlation of these theoretical resilience measures with the empirical ones. And the first question that we will try to answer with this is like, which theoretical resilience metrics measure recovery best? And to do so, we will take averages across all our vegetation products that we use. So what you will see in this plot is actually on the y-axis, the average Pearson correlation, average because it's averaged across all vegetation products, as I said. And on the x-axis, we have like the goodness of fit of the actual empirical recovery rate. So the higher, the better the empirical, the pink line fitted the other one. And the colors now will be the different resilience metrics that we are using. We will look at lambda GLSAR. This is like a regression that takes correlated noise into account, and then a corrected variance and autocorrelation. And these are the results. So what you can see here is that lambda GLSAR and autocorrelation actually perform best, and that the corrected variance, even though it's corrected for the noise amplitude, performs a bit less good. So these are the results comparing the resilience metrics. Now, the other question is that we can ask is like, in which data sets can these theoretical resilience metrics actually measure recovery best? And now we will just have like exactly the same results, just that it's not averaged across vegetation products. So yeah, here now you see again, like on the y-axis, the correlation coefficient, and on the x-axis, all the different products that we are using. And you can see now, like, this is only for the lambda GLSAR, but of course we would have the results for the other ones as well. It's just too much to show. So, and what you can see here now is that the best data sets that we might find, or in which it is most possible to actually estimate recovery with those theoretical metrics, is NDVI here. Actually, this other one is almost the same, so we only will use NDVI. And these four here in the end, like CVOD from AMSE, and C1, C2 VOD from AMSE2, and the LVOD from ESMOS. So now we can actually try to answer the question, like, does resilience change in the tropics? So we will use exactly this one indicator, the lambda GLSAR, and those 5 data sets that we have used, that we found to be the best. And we look at spatial averages here now for the 3 tropical regions. And these are the results. So this is the Amazon rainforest, the African and the Asian. And the different colors are the different vegetation products. And so what I found very interesting is that they actually agree very much in the general trends or the general behavior of this lambda GLSAR, even though they are really from completely different sensors, wavelengths, whatever. So yeah, this is the first conclusion from this. And the second one is, I guess one can see some resilience loss, especially pronounced until the year 2018. And then we don't really know how it goes until now, because we can't exclude human land use changes in the last 2 years. So that's the results. And we will now conclude with a short summary. We started with the ingredients and the potential obstacles and saw that like noise can bias the resilience metrics and data can be problematic. So the first idea was to investigate the noise. And we found that it's not really what we would hope for from a theoretical perspective of resilience analysis. And next we checked if the theoretical metrics actually measure recovery, and we could find that lambda GLSAR and AC1 perform best, at least in our case. And also in our case, the 5 best data sets were these 5. So then when we looked at an average lambda GLSAR across time, we could find that like for these completely different vegetation products, actually they pretty well agreed on resilience changes. So what we would conclude from this is like if you get the right combination of data and resilience metrics, then you can actually do resilience analysis for tropical rainforests that are robust. And yeah, there was resilience decrease most pronounced until the year 2018. So that's it. Thank you very much. I'm happy to take any questions like that.
Thank you.